Okay, I think let's start with opinion thing.
Yeah.
Okay, can you see my screen?
Yeah.
For the opinion, this is oh, this is the map over the Barnett interval. For the final row B, I think over there is a looking fine, but I saw a little bit blue eye on the whole one world. It seemed like more than row B than this other whales. So I don't know. I don't know. I heard you said the whole one whale is it could be have more carbonate over the north area, right?
Yeah, so when you look at average values for stuff, there's so many different kinds of ways to plot up petrophysical things, right?
Mm-hmm.
Like you almost kind of need to sit down with a piece of paper sometimes and figure out what it is that you're trying to map, and then actually write an equation or something on paper to get you what you need. So, for example, let's do that exercise, right? I mean, geologists tend to get crazy with mapping a lot of times where they just start mapping everything up and trying to do
Mm-hmm.
overlays and compare maps and figure out, what all of these different properties are telling them. But really, like you've got, for example, let's just list the properties, right, that could impact our analysis. One is the data quality itself. So if we have to recreate a lot of data in that whole one well,
Mhm.
Is it pushing our answer one way or the other? So, for example, let's say one of the key properties is the net feet of limestone per well, right? So if you mapped that, what would that tell you? So, so yeah, let's look at this for a second. So the whole well is fairly washed out.
Yep.
But it appears that there's a pretty big interval there.
All right. Mm-hmm.
The other thing is that the tops are a bit strange here compared to like it's considerably thicker. Right?
Oh, because
I
the
think
other
the reason
whale.
for that is
Yeah.
you're breaking off the Chester, right? So we need to do the same thing here
Mm-hmm.
with that top, is break out the Chester so that the Barnett is actually the Barnett at the base of it. And that's going to change your numbers a bit. But with that being said, I mean, still, let's think about the equation that we want to write down on paper. So we grab a piece of paper here. Yeah.
So
The key things that we'd be looking at, for example, is we want to look at the average bulk density. Okay.
Mhm.
What that's telling us is, the petrophysical log properties over that top, well to well, if there's any substantial changes that would pick up. If you look at the gamma ray, right? The gamma ray is pretty consistent over that Barnett pick. There seems to be like a little knife edge that's coming in towards the base, maybe a third up with a higher resistivity peak on some of the wells,
Oh,
stuff like
it's
that.
hard.
Like that's,
It's hard to see in over the whole well, whole one well.
yeah, but you can still kind of see it on all of them. It tracks, you know,
Mm-hmm.
correlates stratigraphically from one to the other. Um, so, you know, that's kind of indicating that as far as I can see, that you know, the amount of deposition going
Mhm.
from west to east between that little knife edge at the bottom, it looks like it's thinning.
Right.
So as you head north, the Barnett Shale is thinning, right? Which is kind of what we expect to have happen, because the further north that we move,
Uh-huh.
you know, the shallower we're getting. Like if we look at
Uh.
the depths on these logs, which are really difficult to see if not present at all, but what is the depth difference? I mean, if you flatten that cross section on the Mississippi line,
Mississippi. Okay.
which would, which would truly flatten it, because right now you're kind of that miss line to the miss line.
Oh, Miss Lam. Okay.
Okay, so what is the depth of the miss line pick in the hole one?
Oh, one is around
12,000 feet, let's say.
Yeah.
What is the depth on the Scarbauer? So it's 500 feet deeper,
Mm.
right?
Yep.
And when you're talking about, well, again, I don't know the depositional model and proximity to source for this one, because this is like low energy sort of, I don't know what you would call it, right? Pelagic
Yeah.
crap, you know, like just low energy sediment settling
Mhm.
and condensing underneath, you know, in an anoxic environment, reducing environment. So you've got those organics. The other thing that looks a bit weird is that the resistivity itself, even
Yeah.
though
Right.
that bottom Barnett section is not washed out too badly,
Mhm. Mm.
seems to have much lower resistivity than the others. So that's telling me that something's changing there as well, and the density seems to be a bit higher. So there's something depositionally going on that might
Mhm.
support your case of a higher density value once you get that top picked properly and all of that sorted. But anyways, so we're looking at average bulk density as an indicator, right? I would say clay volume should be in there, the average clay volume. And you know, that's a function of neutron and sonic as well.
Mhm.
And then I don't know how we lump resistivity in, but one of the things that you can do inside of that mapping program is there something that if you go to that really quickly on go to the
Oh.
interface for it where you make the map.
Yep.
So you've got all these features, right? Gamma ray, neutron, PE, bulk density. You could
Mhm.
even throw resistivity, deep resistivity in there as
Oh.
well.
Right. Okay.
And then check the log 10 on the deep resistivity. And now select from the statistical method on the top and go all the way down to neighbor distance metric. I think is the one at the top.
Neighbor. This. Okay.
And then change in the search radius to like 50 miles or something. So, you know, 50, 50, I'll say.
Oh, 50. Again. Okay.
So this is one way of kind of doing what I was talking about in an easier fashion, is that this is a correlation now that's between all of the different features that you input. right? So all of those things get added together. And the reason that we wanted to do a logarithm of the resistivity is so it doesn't dominate the response.
Mhm.
And then it's looking at how similar each well is to each other in that 50-mile
Ah.
search radius, which should be big enough for the area that we're working. And we see that there's basically
Mhm.
a range, which is not too terrible, but from a 0.58 to a point, or you could just say from a 0.6 to a 0.7, sort of R squared. And, the basin wells. So if I were to read this, read this map, the way that I see it is that the basin wells kind of all agree with each other,
Right.
and the platform wells sort of agree with each other, except for the University 7 Berkeley. That one is the outlier because it doesn't look like the ones near it.
Mm.
Does that make sense?
Yeah,
So that's
makes
if
sense.
I was looking at these wells, that would be the one that I would look at. Now, the other problem is obviously the top that you put in there is still incorrect.
Mhm.
So we need to fix that top, and then rerun this. But that's one way to check all the different inputs that you have to see the similarity between them once you've got the wells fixed. Now, you ran the multi-well auto edit on this one or not?
Not. I already do a full petrophysics, so I don't know why we need to run multi-well auto edit again.
Well, the reason being that I was going to say is if the data in the Barnett interval is really bad condition, another answer to compare to, which may show you something that's a little bit different than what you thought. So normally when I work the Barnett and really washed out wells, I have a really hard time reconstructing data. Like I said, the
Mhm.
approach that I normally use is I go down to, resistivity and the normalized environmentally corrected gamma ray. And that's all that I've got to work with to reconstruct density. And then once I fix density, then I got to use those curves to reconstruct neutron and so forth and so on, right? Auto edit multi-well does that automatically. So you don't have to do it one at a time. And it may, again, I mean, to go back to your cross section, right?
Okay.
It all depends on how bad the data is. Yeah, so I mean, you've got calipers that look like they might be okay in some of the wells, but look at the density correction. It's just as bad
Yeah,
for the
right.
most part, like in the Fasken David and the Scarbauer as it is in any of the rest. Probably the best looking well that you've got there on the batch is the Holt, one with the higher density. So once you get tops sorted, then what I would do is just kind of run those super duper plot thing over those two tops, the Barnett and the Chester, and then create another set of bad hole flags
Mhm.
that really discriminates hard. Like don't include data that might be bad, only include good data. And I think your bad hole flags there already look like that most of the interval has been flagged as bad hole. So I don't know. You have to include more wells in your thing in your cross plot. And then in the multi-well auto edit, if you go to the apps menu and you run
Mhm.
that,
Oh.
it's the top one. Yeah.
Oh.
So this thing has got a pile of shit in it, but what you would do is you'd add the gamma ray and the environmentally corrected normalized gamma ray and resistivity for the no edit curves box on the upper middle of the screen. And then you provide a 0 in there for the bad hole flags. So, you're basically telling it that all of the data is
Will
good.
would
And then for the edit curves, you would add each one in there and you're gonna enter the XPD, for density. That'd be the first curve you put in.
Mhm.
And then for the regressors, I would select like GBM for the regressor, which is the decision tree based algorithm. And then you can run this. You don't
Mhm.
need to select, all of the wells for editing. You just select which wells
One
you
well.
think have the best data.
Oh, yeah.
And I would select probably all of the wells with those band flights for the training data. And then just select the wells that you want to edit for the editing wells. And then just run this and put it in a separate set. Right, so your
Mm.
output set would be like the
Mhm.
auto-edit multi-well set or something, so you don't overwrite or clobber the
Ah.
existing interpretation you've got. And then plot the curves that come out of this against the curves that you have in your final set. And just take a look at them,
Mhm.
and
Yep.
see what they look like. What you might find is that the density could be much higher that comes out of
Mhm.
this than what you already have, or it could be different, whatever. But this is the general approach that I
Mm.
would take. And the
Okay.
other thing about this program is if you're missing data, this program
Mm.
automatically synthesizes it. So
Oh.
say, for example, you've got 2 or 3 wells that have sonic data, and you've got 2 or 3 wells that don't. When you run it, it'll automatically generate sonic data in the wells that don't have sonic data, and it will use the correlations that it finds from the wells with the sonic data. It automatically does this, hence the name auto edit, right? So when
Mhm.
you're done, you'll wind up with new synthetic PE, synthetic sonic, whatever you're missing. And it's using the decision trees to do it, which is the same stuff that's in the MLNet program. The only difference here is that here you have like a static hyperparameter configuration for the MLNet, where
Mhm.
in the program you can, it changes, it does like a grid search on the hyperparameters. So here, like the defaults will probably work just fine, but we need to eyeball it, just look at it and see you know, what it looks like. But
Okay.
this is how I would handle it, right? I would fix the tops first, then I would run this. And
Mhm.
once you get the output and you compare it, that's
Yep.
when you have to make an executive decision on what to change or splice, if anything at all. And if you
Mm.
do, then you just rerun those new curves through the vClay interpretation
Ah.
and run it through Mineral Solver, right? You have to redo your U and all that stuff. And then, you'll have an answer, and then you can start mapping, uh, even some of the output curves using that vapor distance metric, like this porosity, saturation, everything else. It'll tell you how similar or dissimilar the wells are. And what I would expect to see in a map like that is a trend, a
Mm.
geologic trend,
Yep.
right? I expect to see things on the platform are going to behave differently from things in the basin, and things in the basin that are more basin centric and to the south are going to look different compared to how it moves north. When it moves north, right, you're going to have to
Mhm.
include more wells in this map, include all of
Okay.
the wells, right?
Yep.
But when you do that, you should see that something's changing as you get up into the northern part of Andrews and Martin County, where that Barnett Shale is starting to disappear. Right, there's something happening there.
Yeah. Right.
And you can also make some net thickness maps and some other things in there as well. And that's the question that Eric's trying to answer, that he needs to put in his slides and stuff
Okay.
for this investor presentation, right? Is they want to compare how different the Barnett Shale is in this area where you're at, like the Scarbauer and that glass, because they know that Oxy and some other operators have drilled successful wells there, and they know that it works there. What they don't
Mhm.
know is what's happening where that well is in the north, right? That old 1950s well, I forget the name of it.
State BR. Right.
state BR well, right?
Yep.
So, you know, Eric is a geologist, so you want to
Mm.
give him something that's geological that shows him a trend of here's what's
Okay.
happening in this interval moving, from the south part of the basin to the north. Separately from that, a completely different thing is going to happen on the plateau. But we're sort of interested in what's happening in the basin proper, going from the south to the north. And you should see something happening there. So, once you get that done, and really kind of the way that I approach these sort of things now,
Mm.
having worked this shit for 20 years, is you almost kind of want to reverse engineer it. That's the process that you take. So, instead of just hunkering down and doing analysis from well to well and looking at the results and trying to map the results and trying to figure out where the bullseyes are and all this shit, right?
Mm-hmm.
It's almost better to come up with the geologic trend first and then sort of conform all of the wells to that so that it makes a nice map and that we don't have to worry about bullseyes because we sort of figured that out to begin with. And one of the ways to do that is with this auto edit multi-well stuff and other
Okay.
things, right?
Yep.
So it'll save you a lot of pain in the end because you'll be able to identify really quickly, like if I've got a trend going on, which I should
Mhm.
have, right? The
Mm.
stuff that's more in the center of the basin should be much more clay rich and organic rich, higher resistivity. As you move north, you're getting into these limestone things, right? And different type of deposition. You're losing some of your siliclastics
Mhm.
and you're losing that anoxic environment, which doesn't have as much preservation of the source rock.
Yeah.
So, if I've got a well that sits outside of that for some reason on my map, like it's just a bullseye, then I need to ask myself the question of why. Is it a
Mhm.
data quality issue? Is that well really badly washed out? And I did all kinds of work to
Mhm.
reconstruct that data. And despite
Yeah.
my best efforts, it just didn't come out right. And this
Mhm.
this goes to, the point that Daniel made a while ago about this, which I sort of agree with him on, not fully, but sort of, is that if you have really bad data, we probably shouldn't use it for
Mm.
this reason. Because no matter what you do with it, it's not helpful or useful because when you compute everything, you get a bad answer, and then you've got to spend all this time fixing it, normalizing it, and editing it, fucking with it to get it to fit your map. But it didn't provide any control on the contouring of the
Right.
map, right? We're just,
Yep.
I mean, we could just create a whole bunch of synthetic wells, just fucking make up data and all of them too, and force it to fit the map.
Mm.
And that's not what we want to do. So some of the wells we may
Yes.
have to just legitimately flag as being anomalous. They're just so fucked up that we can't do nothing with them to cost. And where this is going to go, the reason I'm wasting all this time talking about this stuff
Mm.
is because we're going to end up doing the same thing,
Right.
most likely, for all of those wells from Diamondback. So when we get into that, right, I've already talked to Corey about it. He seems to be pretty interested in trying to repair and fix a lot of those wells that are in the medium category that you had in your slides, right? You've got like good, bad, and ugly. So the goods, we got 16 or 17 or whatever, right? We use
Mhm.
the
Right.
goods to try to fix the bads and we throw the uglies away. We don't mess with them because at that point, all we're doing is a normalization exercise that doesn't mean anything. So same approach, right? How do we do that? We take the 17 goods, we run multi-well auto edit, but in order for that to work, we need to make sure that we very carefully normalized and environmentally corrected all the curves that we can because it's so washed out. And I think there's even some environmental corrections for the resistivity as well. Like if you go up to the edit menu, I think, or calculations menu, and IP, really quickly.
Okay.
And then go down from environmental corrections on the bottom, and I think there's one for Schlumberger, just pick that on the top. So we're familiar with the gamma ray tab here, right? But there's also like, you know, there's induction, there's dual lateral log. So like if you click on the dual lateral log one, the far right one, it says DLL, MSFL, MLL. Click on that. Right,
What
so
it is.
yeah, so now you can do like, you know, you can input a caliper, you can input, you know, the same sort of things where you've got your different resistivity curves, and you can input what the, you know, the mud properties are, and you can try to environmentally correct the resistivity tool. So this goes back to like that numerical modeling stuff that I showed for the density, right? If we know the depth of investigation of the tool, and we know that there's a shallow, or I'm sorry, there's a near and there's a far detector, right? And we know that the geometric factor of the reading of the tool based off of the source intensity and the configuration of the tool, there's a certain percentage of the signal that the tool measures that comes from the wellbore, right? So in the case of a density tool, like what do we do to fix that? We put the fucking density tool up against the wellbore. Right? That's how we fix that. We center the tool. And by doing that, we reduce the, you know, the depth of investigation that's contaminated by the wellbore fluid. Because now the sensor is in direct contact with the rock. But what happens if there's washouts or filter cake buildup, right? So now I can't remove that. How do I remove it? I put a skid on the tool. So on the density tool pad, there's a plow on the top of that skid, and that plow is designed to remove mud cake from the wellbore wall as the tool goes up the well. Okay, what happens if I got a big washout and there's like a whole bunch of shit packed in there, and fluid and mud cake and other things?
Yep.
Now what do I do? Well, now I'm fucked. At that point, now you've got a density correction curve, a D-row curve, and it's telling you, you know, how much it's seeing a difference between the short space and the long space detector.
Yes.
Okay, what about resistivity? I've got a lateral log tool, right? I don't know that we did we do a resistivity one yet? I don't know that we did. But
we did it.
yeah, so we'll have to do one of those at some point. But resistivity
Okay.
tools for an induction log, right? You've got different math, different stuff going on. But for a lateral log, you've got a current that you're injecting into the formation at the bottom of the tool with electrodes. And you've got these bucking electrodes are called that sit around that main source of injection that kind of force that current into the formation. And then you've got sensors, just like a sonic tool, kind of, right? Like where you got the transmitter at the bottom, you got the receivers up top. Depending on which receiver, you get a different depth of investigation. So for a lateral log tool, that's why you have RT10, RT20, RT30, RT40, RT50, RT60, 70, 80, 90. Those are inches of depth of investigation based on the distance between the transmitter, the injecting device, and the receiver array. So the depth of investigation of contamination is similar, right? If you've got a shallow one, like you're looking at RT10, a 10-inch, that thing is going to change a lot more if there's washout compared to the 90. But the 90 is still going to suffer because like 20% of the signal or 30% of the signal is coming from the washout. It's causing the whole resistivity curve to read lower. Okay. So this sort of correction, which is in the chart book, what this does is tries to, you know, you have to tell it, is it centered, is it decentered, which we can find out based off of tool diagrams. Most typically, the tool is going to be centered, right? There's not going to be a 1.5-inch standoff. And then, you input the curves, you input the mud properties, and you
Mhm.
input the caliper curve and the bit size. And if we get
Mm.
all of those things right, then what it tries to do is say, okay, based off of some of these numerical models, I know at this particular depth, I've got a washout that's 2 inches deep. Okay. So I know that that's contaminating my signal. And if
Right.
I know what is in there, right, you tell it what's in there. You say, here's the mud resistivity, here's the mud cake resistivity.
Ah.
So it says, okay, I know what the contents of that washout are filled up with now. So it uses that to run, an analytical, basically electromagnetic flux model to remove that response from the tool reading, which is going to make the resistivity be higher because you're drilling with water-based mud, which is saline and high conductivity,
Mhm.
right?
Right.
Okay. So like these sort of things, I haven't, I normally don't have time to fuck with this either, but uh, I think that it's incredibly important to do this
Mhm.
in this type of project because, you know, we're doing a lot of our data generation
Yeah,
using
right.
only two curves. And those
Yes.
two curves have to be as the best that we can get them,
Mm.
which means, like I say, we have to choose a well that's not fucked up and then use that as our standard for our gamma ray and our resistivity normalization. Be careful about the
Yep.
differences between induction and lateral log. And be careful on how you normalize the gamma ray. For the resistivity, I think I'm less comfortable normalizing it, but I'd like to see what comes out of the environmental corrections, just to see how much it changes the answer, right?
Yep.
So,
Okay. Um, I will follow your approach and compare the result, and then I will add the geology interpretation from the data in my slide. Yeah, and I will update to you. Except,
yeah, like I say, I think the way I would tackle this is step one, kind of run a pilot, if you will, sort of check on the
Mhm.
lateral log correction and just see what it does in one of these wells that has measured lateral log data. And then see how much it changes it. If it's a lot, then, you know, then maybe we should do it on more of the wells that are really washed out.
Yep.
Then run the multi-well auto edit, step two. And you're doing that now with the environmentally corrected normalized gamma ray and the environmentally corrected resistivity. And I would make some histograms and stuff of those curves
Okay.
as well before they go in, just to make sure. And
Yep.
then after that comes out, then what you would do is compare
Mm.
the results from the multi-well auto edit to the final curves that you have.
Yep.
And don't do
Okay.
anything yet, but just look at it, compare it,
Mhm.
plot them, and see what they
Mhm.
look like. And then, if they are different by a
Mm.
lot, that's when we need to, and we can make a map. We can make a map of the final auto edit curves, right, without changing
Right.
our interpretation of them, and see if there's a geologic trend to that.
Uh-huh.
And if there is, then maybe we should use them. You know what I mean? And then rerunning all the rest of the stuff takes minutes. You just gotta
Yeah, right.
copy the curve over. Don't destroy your old stuff. Back it up to a different
Mhm.
set or something. But run a couple multi-line formulas to copy stuff to the final set. Rerun your V clay. Rerun your mineral solver. Okay, done. How much did that change the answer? And that's the other thing we could do
Yeah.
too, is if we really wanted to keep track of all of this, which would be nice to show the client, is that you create a second mineral solver set where
Mhm.
you run the multi-well auto edit curves through it that have been corrected and everything. And you keep the original mineral solver set where the the other curves are. And then you can
Okay.
compare, make two maps, put left and right, of the porosity or something, or net pay or whatever we're gonna map from one approach versus the other.
Mm.
Like this is how much we change things just to let them know. And this is something that, if I was the guy paying you money and you showed me that, I would be impressed. I'd say like, wow, like you didn't just give me an answer, but you really kind of told me, how much things can be fucked up. So that helps me make a decision as well. Where if you see a clear trend, and we also still need to understand, like, what's going on between these basin wells, like the Starbauer and the State BR. So I think that stuff up north, totally different. It's almost like a conventional reservoir to some extent somehow. Because otherwise you're not gonna get all that production volume and rate out of a vertical well with a couple of holes punched in it. These Barnett shale wells are deep, shitty rock that need to be fracked with, big fracks, and they suffer a lot, difficult to produce. So, but there may be some conventional components to this as well. We don't know. Like, why do some
Right.
of these things work so brilliantly, for such a fine grained, shitty basin, mud?
Mm.
Why are they producing at the rates that we're seeing? Like, maybe there is some silt in there or something else going on.
Yeah. Who
And
knows?
Eric is kind of like, yeah, he's digging at it from a different direction, but kind of answering that question in a way, right? Some of the stuff up north has more of the components that are conventional and less of the components that are unconventional. And the stuff in the south is more of the unconventional and less of the conventional. But it's a hybrid system that's sort of mixed. I mean,
Okay.
Vern, Ernest,
Who?
Ernest,
Harness.
Jim Varney,
Crying.
Ernest. It, this is something of my generation. If you go to
Oh,
Google
yeah.
and you type in like Ernest goes to camp or something,
Hermes. How to spell?
ERNEST goes to
ERN.
ERNEST
Oh, okay.
goes to.
Goes to jail.
Yeah, click on Ernest goes to camp. There you go.
Camp.
Yeah, this is Ernest. He says, you know what I mean? You know what I mean, Barn? That's like this catch line.
Oh. Why I can watch
They made
Prime
like they made
Video.
like a dozen. Yeah, there's like a dozen of these things, right? Every one of them was basically the same character, just in a different situation. So like Ernest goes to jail, Ernest goes to camp, Ernest goes to school,
Ah.
Ernest goes to the mall, Ernest goes fishing, Ernest runs Python, Ernest,
Oh, really?
yeah, Jim Varney is the guy's name. He died from cancer a while ago, but his character is Ernest P. Worrell.
You know what
And
I
we
mean?
all we all watched Ernest as kids. You know what I mean, Vern? You know what I mean?
Okay.
Hold on. You got it, Vern.
I got it.
Okay, yeah, I mean, like I said yesterday too, the thing that we should probably do is just work with the cleanest data that we have at the moment. And then we could put together, you know, a workflow showing from start to finish what happens. And then, you know, it's somebody's responsibility to get the rest of the data. And, you know, I can try, we've got the contacts already at Core Lab, so we can beat up on them a little bit more, but if they didn't send it to us already, they probably don't have it. Or it's missing somewhere, and there's been so many people throughout the years that have worked on these projects that retire and quit and everything else that things get lost, you know. But even if we don't have all of it, I think we have enough of it that it's useful. And then, like I was saying earlier, right, one of the key things that I see as an end product that we can work on that delivers quite a bit of value to Diamondback is taking all of this facies work once we get it done and then tying that to core data, to real core data, right? So like permeability, porosity, stuff like that. And we've got all of that for the tight oil. You know, we got all those spreadsheets and stuff I sent you, all that GRI stuff and everything else, TOC. We can tie, you know, the facies. Yeah, we could build correlations by facies that better predict these things. And, you know, maybe come up with some sort of better permeability transform and property transforms that we can use, you know, to help the geologists figure out where the best rock is. And there's lots of different things in those spreadsheets that can be tied to this. It's not just porosity, right? There's shitloads of measurements. The other thing that we've got coming, which I don't know that I've got a login yet, but I think they set me up. Let me just write that down because I forgot about that completely, is this Vidance stuff. So, let's see, Vidance data. Daniel's bitching at me too now. He wants something. See, so the Vidance data. I don't know. Do you guys know what that is? Have you seen that? Did I tell you about that? I think you guys sat in a meeting in Midland there, right? No?
I'm not sure.
Yes. It was a meeting that Weston and Calvin had on the SCM work. It may have been the second trip I made to Midland. You may have not have been there. I forget which trip it was.
Yeah.
Let me see if I can find. So let's look at this. So this is the company. It's called Vidance. They, the guys that run it, Matt Powers, and they're from Canada, from Vancouver. They had another company or worked for another company in the past that was called ChemScan, QEM. And what they were doing was processing SEM images. Okay. And so, you know, they've got this stuff automated now. So what they do is they take cuttings or they prepare samples in epoxy or whatever, right? And then they shave them down so that there's a nice smooth surface to scan with the scanning electron microscope. And I think they bought their own scanning electron microscopes or something that they use. And once they get the data, if you don't know how scanning electron microscopes work, should, by the way, on. So you got the sample there, right? It's in an epoxy block, say that's your little cutting or whatever. So the scanning electron microscope's got a beam, right? Bounces an X-ray off of the thing. You get one back. And this is called backscatter,
Mm.
right?
Yep.
So that's what produces these images, black and white. And the image is black and white because the amount of energy that's reflected has to do with, everything in all of reflection, whether it's sonic reflection or electron reflection, neutron reflection, whatever. It has to do with, even kinetics, right? If you send a small thing against the big thing, right, it comes back with like 99% of the energy that it went in with. If you send a small thing against a small thing, the other small thing goes flying in that direction, right? And this thing loses almost all of its energy, like pool balls when you play billiards or snooker, right? So backscatter electron microscopy looks at imaging, essentially is all that it is. You look at this cool image, you're like, man, what is that? Looks like dust or something. Oh, it's clay, little platelets of clay or halonite or whatever the hell that is. Maybe it is dust. Right? Maybe their laboratory is dirty and they didn't clean the sample, like who knows? But that's what's happening. So you get like bright things and you get dark things that are telling you how much energy came back. And it does all this triangulation stuff to look at the incidence angle of the image scatter and to figure out, where everything is by kind of goniometering this thing. You change the, anyways. The other thing that you could do is you could do EDS. Okay. And EDS stands for energy dispersion spectroscopy. So it's not just looking at a single value. It's looking at spectroscopy. So you've got a curve now, right? Where you've got some spectral, total count rate or whatever, or combination of, this stuff all adds together. Same way like spectral gamma ray, right? You've got a total gamma ray and you've got all these different channels that compose that, right? Depending on the energy level, right? Density is the same way. Density tools got this spectroscopy aspect to it. From that, you can correlate that, okay? Not just to the elemental or to the energy for like black and white, but you correlate the atomic number of the material. And based off of these patterns, because these things are complex, right? It's not just like the electron hits another electron and then bounces back. No, there's a whole atom there, right? That's got all kinds of different composition in it. So when the electron interferes, when it gets absorbed by the atom or whatever, it ejects a new electron that's got properties, right? Through photoelectric absorption, through Compton scattering, the same things that happen with a density tool. It's no different in a way, okay? So you can get density, which is what that is, and you can get PE, okay? And that's kind of what that is in a way. So what they do is they take these signatures, they make these different signatures in a database, and they can figure out what the elemental composition of some of these things are. So they know there's iron, right? They know what that looks like. They know what calcium looks like, copper, whatever. And they can make these maps. They then take it a step further to start to add the elements together to say, well, if I got iron, right, and I've got aluminum, and I've got silicon, and I've got oxygen or something, that is clay, right? If I've got potassium and aluminum and silicon, that is plagioclase, right?
Yeah,
Or
right.
sodium or whatever. If I just got silicon and oxygen, that's quartz. I just got calcium, carbon, and oxygen, that's limestone, right? So reason I'm telling you this is Diamondback has got a whole database of this shit. And they take this and they start to do lithology typing on it. So they say Arcosic sandstone based off of what they find, right? They take the whole sample here, look at all the individual grains and what's in it, and they come up with some sort of lithology. They can also look at this void space and come up with porosity, right? I'm asking them to try to do electrical properties from this based off the tortuosity. They're gonna come up with a lithology volume, right? Gonna say silicon 30%, right? Plagioclase,
Right.
I should say quartz, not silicon. Quartz is 30%, plage is 10%, calcium carbonate, limestone, is 20% cement, whatever. They give you these numbers for all of these samples, and they do it on cuttings. So like, you know, if you've got 5,000 feet, like every 20 feet or something, they're doing a bag, right? All the way down the fucking well. So there's a massive amount of data. Yes, it's gonna be off depth a little bit. Yes, it's not gonna be perfect because the cuttings lag and mixing and how you make your bag samples from whatever's in the shakers and shit like that, you know, mud logging. But we have another huge source of data that we can use for lithology, you know, on top of what we have from the core descriptions and see if it, you know, I don't think we're gonna have overlap. That's the only problem. You know, like we're not gonna have wells where we have both the Vidance data and we have whole core. Because it just doesn't work that way, right? We never had the opportunity to cut cores and do these things, but what we could do and what Calvin can do, and maybe he's already done, is if you find a well with core, right? And you've got the cuttings laying around somewhere in a box from that well. We can send the cuttings in to have them do that. And now we've got the data set that we need, where we have both Vidance data and core lithology descriptions. And if we can tie the two together, right? Now all of a sudden we have an even cheaper, more accessible way to get to lithology using the Vidance data. And it's also, we don't know what this is going to tell us. We may find a whole bunch of interesting shit happens, right? Like if this is the Joe Mill, okay, and we're looking through this thing and we've got these core descriptions, here's the facies, whatever, they don't mean anything. But like the Vidance data is telling us, no, guys, like right here in this interval, and only in that interval, you've got, you know, whatever, a lot of plagioclase or something that makes porosity. And like that's what's driving production right there. That's your JM3. That is really good because it's got whatever this blue stuff is. You know, no other blue stuff anywhere else. It's just here. That's where it is. That's what makes it good. Well, once you figure that out, if there's a correlation, then we look for blue stuff. You'll find it. Wherever you find blue stuff, maybe you find oil. Right? So that's why I mentioned Vidance, because so you can go to their website and you know, they got all these different things too, right? So you got argon ion milling. So that's one of the things that, like, you know, the problem with even polishing a surface, and I did my own SCM work before. So I know what happens, right? You prepare samples, you go down to like a million grit diamond paste on a wheel, and you've got a rough surface. You know, these guys use these extremely precise ion mills, which actually just scrub the surface with an ion beam and remove individual atoms from it. You know, and that's, you get a perfectly flat surface sample, like perfectly flat. So know, that makes some of the data quality a lot higher than what you would get from whatever I did. But this is what that data looks like, right? You get these cuttings. Then they use their, I don't know what they're doing. They used to, I think, because I had a meeting with them the other day, and I don't think they're using AI yet to classify stuff, but they're working on that, like they're trialing it. But, you know, previously, I think it's the same process. So like XRD, you know, you get some sort of spectra that has to be deconvolved where you know what the peaks are for silicon. So you take that out of the thing and whatever is left, keep working on it until it's all gone. And you allocate the different energy peaks to the different elements. So anyway, it's been around for a long time. It works pretty well, but once I get into the website, I'll show you. The cool thing, like I say, is that there's full like rock lithology, you know, and texture descriptions that they provide. So they don't just say like 30% quartz. They say marcosic, feldspathic, sandstone, or whatever, you know, aeolian fucking whatever it is, right? So that's powerful. And I think we can trust the interpretations. I don't think they're that wild. At the very least, like I say, it gives us lithology. So, you know, 30% quartz, 20% limestone, that's something. It doesn't give us texture or description of the rock, you know, geologic description of sorting and grain size and all that kind of stuff. That's secondary interpretation stuff. So work what you can now. And then once I get into that website, I'll do a bulk download of everything and we'll kind of look and see what we got and how that kind of ties to some of the other measurements that we've got. Because we also have wells that have ECS or you know, the downhole XRF elemental spectroscopy. There's also in some of those Excel files I sent you shitloads of XRD data, right? So start tying all these things together to nail down lithology. And really, like I say, what we're looking for is exotic lithology or something that has a fingerprint on production. Help us get a better answer. Like why are some of these things better than others? You know, is there something that we can tell from it and we can tie it to the log somehow? It's always an upscaling exercise. Go from the finest measurements to the coarsest. And then finally, you end up tying it to seismic, which is like, you know, 30-foot fucking resolution or whatever. But okay, one last thing for the Mustang draw stuff. Did you get the logs I sent you? Are those good? Need everything? Got everything that you need there?
Yeah, I got a file, but I didn't put in the database yet.
Okay, yeah, load those up if you can ASAP and see what data
Okay.
is missing or what's in there. Because sometimes Jorge, he gets excited about stuff. He's like, I need these wells, and all it is a sonic log and a gamma ray or something. Like
Yeah.
there's no other data, right? We can't do anything with it. In
Mhm.
which case, normally what I'll do just to keep them happy is just depth shift the sonic data and sort of clean it up a little bit, de-spike it the best you can, and just hand it over, you know.
Yeah.
But you know, we can if it turns out, because I didn't look, I just did a dump out of Kingdom. I didn't go in there and like look at all the last file, so I don't even know what's in there. Could be nothing, could be everything. But do that. See what you find.
Mhm. Okay.
And yeah, just keep plugging away at that stuff. I've got some things I'm working on here for I also updated the program again. Fixed some things with the multiple saving issues that we had. We need to test that out some more and see what happens. I think most of them should be fixed. Maybe we'll try to do that tomorrow or Thursday or something, and then, what else? Added some other stuff to it. I'm in the process of adding more per statistics stuff that wasn't in there before, and for renaming, even easier stuff to use. And, some other things that just weren't working properly, so kind of fixed them. So start testing that out, and then,
Mhm.
what else? Trying to remember what Corey had to say yesterday. I don't know, I think that's it for now. If anything else comes up that's important, I'll send you guys a note on Teams or whatever.
Yeah, okay.
All right.
All
to you
right,
later.
thank you.